Hi everyone. In this part, I'm going to show you how we simulate the tossing game in Excel. Okay, so here in these cells, we had the probability for head or tail. Since we assume a fair coin, so the probability for head and tail will be 0 0.5 equally for both outcomes. Okay, and yeah, here we have the columns, and each row will be for a tossing of the coin. So yeah, we have the toss numbers here. It will be for 100 tosses. Yeah, and okay, so at first for each toss, we need to have the round function to obtain if the toss is head or tail. Okay, so here we generate a random number by the rand function, as you see here, the rand function. And then here, by having this if function, then we say that if b8 is the generated random number, is less than or equal to b3, b3 here is the probability of being head, then the result will be head. Other than that, it will be tail. Okay, so by that if function, we can obtain by the generated random number the outcome of the toss. It will be head or tail. Okay, you see here. Okay, and after having the outcome of the toss, we need to obtain the winner. Okay, so here again we have an if function, and we said that if c8 is the outcome of the toss equals head, then Harry is the winner. Other than that, Tom will be the winner. Okay, so yeah, again here we obtain the winner of each toss here, and then for winning or loss for Harry and Tom, for the first toss, we have if c8 equals head, then Harry will gain $1. Other than that, it will lose $1. Then will be a negative 1, right? And same for the Tom, we'll have if c8 it's equals tail, then Tom will gain $1. Other than that, he will lose $1, so it will be a negative 1, right? For the second, from the second actually tosses, we need to calculate the accumulative values for winning or loss. Okay, so as you see here, for the second row, we have E8, I mean the previous value for the winning or loss of Harry, plus again that if function. Okay, so by having this, we'll have the accumulated value for winning or loss for Harry and Tom. And for the leading, we'll have this again if condition that if f8 here is the Tom's actually number of winning or losses is greater than e8, I mean the number of winning or losses of the Harry, then the leader will be Tom. Tom will be the ahead, right? Else again we have another if condition here. If e8 is greater than f8, then Harry will be the leader, and else it will be even, right? So here we have again the outcome for leading, and we repeat these cells for 100 times. It will be 100 tosses, and you have here actually you have here let me see if it's, yeah, it's recording. Let me close this window. Okay, so now we can obtain the result. Anytime that I refresh the numbers, you see different values here, right? For example, here the number of winning for Harry is 59, the number of winning for Tom is 41, and the final gain or loss, Harry at the end will gain $18, and this means that Tom will lose $18 as well, right? And the frequency of leading, as you see here, Harry is leading in 100 tosses. So this means that Harry is always the leader from the beginning to the end of the game, right? And yeah, that's it. So let's change the numbers again, refresh the numbers, and we have a different result. As you see here, Harry is leader in 38 games, and Tom is leader in 42 games, and they are even in 20 games, right? And we can calculate the probabilities here as well. Okay, so as you see here, this is the simulation of the game for 100 tosses, and as you see here, anytime that we repeat this game for 100 tosses, the results change, right? So this is because of randomness, right? Because we generate a different stream of random numbers at any repetition of the game, right? And because of having different streams of random numbers, the results at the end will be different for each trial, right? So what can we do in order to have somehow robust results? I mean, the results that we can rely on them and they wouldn't change that much if we repeat the game again. We can say we have two options here. We can increase the number of tosses, right? We can increase the number of tosses from 100, let's say, to 400 or 1,000 or 10,000 or maybe 100,000 and so on. So yeah, let's try for 400 tosses and see what happens. So the second sheet is for 400 tosses, and now, for example, for one run, as you see here, Harry is leader in 267 tosses, and Tom is leader in 109 tosses, and they are even in 24 tosses. So let's refresh the number. Again, the results changed. As you see here, Harry is leader in 158 tosses, Tom in 216 tosses, and they are even in 26 tosses. So as you see, by increasing the number of tosses, there is no change again in the outcome. I mean, the results are not robust, and they are changing anytime that we repeat the game. So another approach here will be replication. We can replicate the game of 100 tosses for 100 times, for example, for 400 times, for 1,000 times. So that means replication. We are replicating the game for a certain number. So here let's have replication for 400 times. This means that we are going to replicate the 100 tosses for 400 times, okay? And we expect to have somehow more robust results by having the replication, okay? Replications. So how we do this? In order to replicate the game, we have these columns here, replication number. So the replication number will go from 1 to 400, okay? And the probability of being ahead. So in the 100 tosses, we have the probabilities here, right? N4, N5, and N6 are the probabilities for being Harry ahead, Tom ahead, or they will be even, right? These are, we have the probabilities for 100 tosses here. So we refer here, I mean, the probability of being ahead for Tom, we refer that cell. So yeah, run of N4 in the sheet of run of 100 tosses. For Tom, N5, and for being even, N6, right? These are those cells. Now we should actually select all the cells up to 400 rows, and then we go to data. We go to data and what if analysis. Here we have data table, and in data table we leave the row input cell as blank, and you click in the column input cell, and then you click on any cell other than those cells, on any cells in any cell in the sheet, and then you click the OK, and then it will actually calculate the values for 400 replications. Okay, so we have the numbers here. Let's as you see here, the probability for Harry being ahead is for 0.46, for example, for Tom is 0.46, 0.46 and even 0.07. Let's refresh the numbers. As you see here, the values change, 0.45, 0.47. Yeah, they are changing, but not that much in the 100 tosses. The results are somehow more robust here, okay? So this is how we mitigate with the impact of randomness. In order to decrease the impact of randomness in our results, we need to replicate the simulation for a certain number of replications, and then by doing so we are actually decreasing or eliminating the impact of uncertainty or stochastic on our result. Okay, so yeah, this is actually the simulation of that the tossing game, which is a Monte Carlo simulation in Excel. And as you see here, it's so easy, and especially for the Monte Carlo simulation, it's not difficult, and we can definitely implement any Monte Carlo simulation in Excel very easily, actually. But yeah, in the next example that we have in Excel, you will see a discrete event simulation model, and we'll see how we implement that kind of simulation in Excel as well. Okay, thank you.